Welcome back. In section 7.4.2, we'll be looking at the dimension of a span. So let's start this in this video. As we've seen in the previous section, a span does not have a unique basis. We've seen in general that if you have a non-trivial span, it's going to have infinitely many bases, and we've looked at examples and found a few. In fact, any set of two non-parallel vectors in R2 gives a basis for R2. That was one of the examples we looked at. Similarly, if you look at R3, you would need three non-coplanar vectors forms a basis for R3. Notice that even though the bases are not unique, they all have the same number of elements. So it seems like the basis itself is not that important. You can find a basis, you could find a different basis, there's no way of choosing, but the number of element in the basis, that's going to tell us something about the span. Alright, so let's look at that. Theorem 7.4.2, let S be a span and let B1 and B2 be bases. So I have a basis with K element and a basis with R element. Then we're going to prove that K equals R. Alright, so that tells you that the bases might be different, but they all have the same number of elements, so the number of generators, that's going to be fixed for your span. Alright, so let's prove this. Proof. We will show that, first of all, I'm going to start by showing that K is bigger than R. The same argument, if I flip the order of the set, a similar argument shows that R is bigger than K, and so R equals K is claimed. Alright, let's start. I have B1 and B2. Since they are bases, they are linearly independent. And so if I start and put V1, V2, Vk, and I reduce this, they're linearly independent, so I'm going to have a unique solution and all of this, or if you want, they're a basis, and so I'm going to get a leading one for each vector, and then depending on what Rn we're in, I'm going to get rows of zeros maybe at the bottom. So here I'm going to get K leading ones. And if I do the same thing with W, the same thing's going to happen. So if I start with W1, WR, and I reduce, I'm going to get maybe rows of zeros at the bottom. And so I'm going to have R leading ones here. All right. So that uses the fact that they're linearly independent. Now I'm going to use the fact that each one span S. So since WI is in S, which is the span of B1, so I'm using the fact that B1 is a basis. That means that WI, I can write it as a linear combination of V1 through Vk. So I need some coefficients. This is more about fixing some indices. So the coefficient of Wi in front of V1 will be A1i, and so here that'll be AKI for A1i, AKI in R for sum. So that means that if I start with V1, Vk here, and I try to write Wi as a linear combination of them, if I reduce this, I'm going to get 1, 1, just like we said earlier. Might be more. And then, sorry, this was meant to be a straight line. And then I'm going to get these coefficients in the constant column because these will be my solutions. In fact, when I reduce this, I can use exactly the same row operation as I did over here. So let's call this star. So if I apply these row operations, so following these row operations, if I start with W1, with WR, if I start reducing this, I'm going to get, so the same as star, well, I'm going to get these. So I'm going to get A11, AK1, 0, 0, A1R, AKR, 0, 0. So if I apply the row operations that got this matrix simplified, but I apply it to this one, what we'll get is we'll still get a bunch of rows of zeros, and then we'll get these coefficients up top. But notice that here, I only have k rows that are non-zero. Everything else is 0. And so if I keep reducing this, if I go to RREF, well, that's going to be the RREF of the W's, and so it's going to be this with R non-zero rows. But if I started with K, wait, is that K? If I started with K non-zero rows, and I reduce to RREF, I can't get more than K's. And so here, I end up with at most K, maybe less. All right, so I've shown one direction, and then the same idea in reverse will give you the other one. So if I apply exactly the same reasoning with WN, oh no, that's right. Sorry, I thought I had it backwards, but it's just the order is, and the sign is flipped. All right, perfect. Good. All right, so we proved that if I have two different bases, then the number of elements in these bases is the same, even though the elements themselves might be different. All right, so we'll use that in the next video.